Well, I understood my name, so I think that means I'm in the right room. And I didn't understand the language, which I think means I'm in the right country. So I think we're good to go. So, Postgres replication. I also think it's 2017. If anyone's off on that, then just let me know after the talk. Could we get the music maybe turned off? Seems... Otherwise, I'm going to have a couple of you people, like the people I know in here, just come up here and do a little dance. Yeah, well, I'll try to get started in it. Let me know if you can't hear what I'm saying. Anyway, my name is, as said, Magnus Hagander. I work for a company called Redpill Linpro, which is over in Sweden. Actually, the company is in all of Scandinavia, but I'm out of Sweden myself, where I work as a database consultant and developer and teacher and all sorts of things like that. Within Postgres, I'm a member of the Postgres core team. I'm one of the committers, and I'm also currently the president of Postgres Europe. There we go. Excellent. Now you can all go properly fall asleep without getting disturbed by, the visions of dancing DBAs. Okay, so we're here today to talk about replication. Who in here today is a user of Postgres? Let's start by that, some level or other. Okay, there's a fair amount of you. What did the rest of you use? So who here was around when we used to say this, or when we used to hear this? Postgres doesn't have replication. So we have to use MySQL. Right? I mean, that's one argument. Or was one argument. It was actually surprising how often you heard this argument a number of years ago, where basically Postgres doesn't have replications, we have to use MySQL. It turned out MySQL did have replication built in. It didn't work, but they had MySQL, they had replication built in. It worked for the simple scenarios. Postgres didn't have it built in. But it wasn't really true back then, because Postgres had replication, it just wasn't built in. And it certainly isn't true now, because now we have it built in, as I'm sure many of you know. The possible problem now is on the other end of the spectrum, more being that we have too many choices now. There are too many different ways to do replication in your Postgres systems. And the fact is that some of them are not exactly easy to use. Some of them are easy to use, and you get to choose between those. Now, as a general rule, if you sort of take a step back, replication can be done at a whole lot of different levels. Anywhere from like hardware, or, I mean, who actually has hardware today? Even if you think you have hardware, there is a big fat layer of software sitting on top of your hardware that you just can't touch it, so we call it hardware. Or maybe we call it firmware, but it's still software. All the way up to we're seeing people deploying today, where you do all the replication in your application layer. Just take care of it and, don't trust the database to do any of that. So if you look at it, okay, we're back. We can actually have replication at basically like all these different layers. We can talk about the application. We can build an application level replication, and we can just store the application code to do that in the database. Oops, so that's good. So we have some technical difficulties with the system here, let's put it like that. So some of my slides may not actually exist. So I'll try to remember the contents of those. So we can talk about the application replication living in database is what we typically refer to as trigger-based replication. So any system where you basically put triggers on all your tables to collect all the changes and then replicate those. That would be what I would call an application code living in the database using for your replication. We can use database level logical replication. We can use database level physical replication. We can use an operating system level replication, like your typical DRBD replicated disks. Or we can do hardware-based replication, which we can then discuss whether it's actually hardware or firmware, but it's a black box level replication sitting beneath all of your system. And if you're doing this in Postgres, you have solutions at all these different levels. So now you just have to choose. Obviously, they all come with drawbacks, and some of them actually come with advantages. So if we start from the bottom at the different options here. So the bottom of your software stack, what you have at the very bottom is some sort of storage, right? And what we're typically seeing here is seeing more and more people deploy on SAN-based replication. So you have a big expensive SAN somewhere, it has functionality to mirror all your disks to a second data center and things like that. Where, as you say, hardware takes care of the replication, except of course it's not hardware, it's software. It's just software that gets shipped in a big box and is very expensive, and you can't touch it and upgrade it or anything like that. The idea behind it, it's block level transparent. So when Postgres or the operating system talks to your SAN, it looks like it's just a disk. And then it's up to the SAN to take care of replication and storing this in multiple locations and failover and all that stuff. It's not your problem. We see this very commonly in large enterprises. Especially the thing that we see a lot of today is deploying virtual machines on these solutions to get like these super high availability. You can get these from single rack to multi-site. They're typically synchronous, and the whole point of them is they're guaranteed to never fail, right? Who believes that guarantee? I see one hand go up, and it's because he used to work for a storage company. The point is, yeah, they're guaranteed to never fail, and you build your infrastructure on the promise that they will never fail, and then they fail. There are many good use cases for SAN replication, but I would say today it's like never a replacement for a database level replication, because if you get sort of any bug at any layer in the system, it will replicate. And like all your copies of your data will all be corrupt at the same time. So at least they're consistently corrupt, but that's probably not what you wanted. Now there are advantages to doing the SAN level replication, which is if you're a DBA or a developer or anything like that, you just don't have to care. It's somebody else's problem. But that's really the main advantage of using SAN replication, is that it becomes somebody else's problem. It becomes a problem of the storage infrastructure. And if you can make that work, then everything else works. But so far, I've not come across anyone who's actually managed to get that to work. As in, every larger customer I've worked with who've used this have at some point have had issues with it, as in data loss level issues, which you probably don't want to do. It also tends to be very expensive, which may or may not be a problem depending on what organization you're working in. If we move further up, we can look at the operating system level, where we typically have things like DRBD being the most commonly known one and the one that we use in the Linux ecosystem. It's very similar. It's basically a operating system level emulated SAN replication. DRBD is something like direct replicated block device, where it shows up as a block device to the operating system, and you just create your file system on top of it. And then the DRBD software takes care of doing block level replication between the nodes in the system. And it, in theory, actually has better availability than your typical SAN-based failover, because you have completely independent copies. But you also tend to get a pretty heavy performance hit from DRBD, at least for anything that does writes. Okay, if all your database ever does is reads, DRBD is actually surprisingly good. But if all your database ever does is reads, do you really have a database? At some point you have to write data into it, otherwise it's empty. And on write performance, it tends to be, it introduces a lot of latency. And you can get a lot of bad performance coming out of that side. So DRBD today, I think, is a solution only if you have like really small databases or write unintensive. Now going up from that, we get into database physical and then database logical. So now we're getting into the parts where we're actually using Postgres to do this stuff. Database physical replication, as we look at it in Postgres, and as we look at it in most other databases, is based on WAL. So WAL replication, transaction log replication. Postgres has had this officially from 8.3. You could actually make it work before that, but there were some quirks. So from 8.3, it was supported. At that point, we replicated in blocks of transaction log files. So each replication unit was a block of 16 megabytes worth of changes. So it solved some problems, but not that many. Since Postgres 9.0, we have streaming transaction log-based replication, where the unit of replication is now a single byte of transaction, and we send it over to the other nodes. As of 9.1, we have synchronous levels, and we can do transaction level mixing. So you can mix synchronous and asynchronous things in the same system, even between the same two nodes. These are obviously things that you can never reach if you do replication at the SAN level. Because if you do it at the storage level, all you see are disk blocks. You don't know what they are. They're just disk blocks. But when we're doing the replication in the database, we can know exactly what the different blocks are and replicate them with different requirements and different characteristics. So this has been sort of one of the main things that Postgres has been going forward. You've seen improvements in this area in pretty much every version of Postgres since 8.0. Right? You've seen more and more options to do physical database level replication. And basically it all comes down to this, right? You set your WAL level to replica. If you were using Postgres earlier versions, you would set your WAL level to hot standby. It's the same thing. And then you build on top of that. And you set exactly the requirements you need. For example, you set your synchronous mode, which you can choose individually for every transaction in the system if you want. Obviously, you set a default level at some point, but you say, do I want everything to be completely asynchronous? Do I want local synchronous, which means my local database behaves like it used to behave, but my replication is asynchronous? Or you turn it on, which will make every commit synchronous. Every commit that has synchronous mode in on will then write to your local disk and synchronize to the local disk and write to the other server that you're replicating to and synchronize to the disk over on the other server. And once all that is done, your application keeps going. These things obviously come with some overhead, but you get the availability. And as of recent versions, you can also have a synchronous mode called remote apply, where we not just replicate the data to the other node, we wait for it to actually be replayed and available to users of the database on the other side before we release your transaction and your application can keep moving. So you have a very strong ability to mix these different levels for different parts of your application, which makes this a very, very flexible way to do replication between your nodes. This really should be everybody's primary choice today. Setting up streaming replication in Postgres is very easy. And in particular, it's really hard to get it wrong in that you set it up so it looks like it's working, but it isn't. That's actually very hard. Setting it up so it just doesn't work, sure, you can always manage to do that, but then you will know that it didn't work. The real danger is when you set up something and it looks like it's working, but then when you need to do a failover at some point, it turns out, oh, it wasn't actually working. Right? That's the problem. It's very efficient. The overhead of doing this type of replication is close to zero. Obviously, you have to actually transmit the data. There is some overhead, but it's a very, very low overhead. And it's built in. Right? So you can no longer claim that Postgres doesn't have replication, because it's right there. It doesn't solve all your problems. It definitely has some drawbacks. But basically, to get it set up, you need two commands. This would be on your typical Red Hat or CentOS machine. You run the pg-base backup command. You give it where do you want your data. Varlib PGSQL would be the default directory on a Red Hat system. You tell it the host name of your master, the user that you want to connect to. Obviously, you shouldn't do like I do here and have no password for your replication connection, but I could claim I had like a .pg pass file or something, right? You'd all fall for that. But in fairness, I didn't. I was using no password. You add the stream the xlog so that you get a fully working cluster on the other side once you're done. You tell it the little magic R flag, which says, I'm setting up a replica. And if you give it that, pg-base backup will write all the configuration files and everything you need to make this directory, that we specified up here, a replica. And finally, you enable a replication slot. In this case, I just call it replica 1, to make sure that the system will keep track of this replica so we don't end up deleting data that the replica needed or anything like that. And once this pg-base backup is finished, you just start your service and you're done. Anyone who set up this Postgres replication back on, say, 8.4 or even 9.0 we'll realize that used to be a lot more steps. And there were a lot of things that could go wrong. This is actually really hard to get wrong. And if something goes wrong in this step, well, you'll get an error with an error code that tells you something went wrong, so you will know it was wrong. And of course, you start your server, well, you have to monitor that it's running after that. There's nothing we can do around that part. But once you have that, your streaming replication is up and running. The one argument I didn't mention, the -p there, that's just to get a progress report as it's building the replica. If you have a large system, I mean, if you have a multi-terabyte database, yeah, it'll take a while to copy several terabytes of data. But once it's done, you have a replica. It is that simple. Of course, there is no such thing as a free lunch. There are some drawbacks to this. For example, if you're using the streaming replication, it has to be the same architecture and the same compiler flags. So you have to you can't replicate between 32 and 64-bit. And you can't replicate between Spark and Intel, because they have different endianness. You must have compiled Postgres in a similar way. Now, this is designed for things like high availability, so normally you're replicating between similar machines, so you're probably replicating from Red Hat to Red Hat, for example. You can perfectly fine replicate, say, between Red Hat and Debian. The issue is all your paths must be the same. So on one of the two systems, you have to decide to go with non-standard paths, because the standard is different. But other than that, it works fine. It's whole cluster only. So it will replicate everything in your Postgres instance, whether you like to or not. So you can't say just this database or just these tables. It'll do everything. And your standby will be completely read-only. And that's, again, whole cluster. So it's not like your, you can say, oh, the replicated tables are read-only. That makes sense. But no, you can't create separate tables either. You can't even create temp tables on the standby. It's completely read-only all the way through. And it's master standby only. You can have multiple standbys. You can have cascading standbys, so you replicate from A to B and then onwards from B to C, for example. That all works, but there can only be one master. But if you consider availability, like uptime level availability, this is actually not a problem, because you typically want all of your database to be available, not just parts of it. And again, since you want to be able to do a failover and maintain application functionality, you probably have a standby machine that has approximately the same specs as the master. It's a classic mistake otherwise, saying, oh, this is just a standby machine. It only needs 1/3 the RAM of the master, which is fine until you actually fail over to it and put your application load on it, and suddenly it's not a standby anymore. So when we are building high availability replication systems, most of these things really aren't problems. They're fine. Now, there are still some issues around it. Postgres does not come with any built-in cluster management, whether automatic or manual or anything. Postgres comes with the infrastructure to do this. We come with a command to promote a standby node to a master. There is nothing in Postgres that helps you decide when to do that. There is nothing in Postgres that also demotes the old master. We leave that to somebody else. So Postgres provides the infrastructure for it. Postgres does not provide easy failback, right? Once you can promote an old standby to become a master, but you can't demote an old master to become a standby. At least not easily. There are some tools around this again, but Postgres provides the infrastructure to do this. It doesn't provide you with neat tools at this point to actually manage it. For the reasonably simple deployments, that's not a real problem, because it's easy to deal with these things, but in a more complex environment, it gets hard. So you end up in the hole, it's easy to get started, but once you've run it for a while, it can be pretty hard to maintain, at least on a generic scale. Most people end up writing their own little management scripts or their own little, Ansible playbooks or whatever you're using. So that thing keeps cutting out every now and then. So you can do that. So that's what you get with Postgres built-in, right? There are cluster management tools. Okay, let's try the other microphone. See if that works better. See if the problem is in that one. I promise I wasn't just pressing the mute button. So there are many different cluster management tools out there for Postgres today. There are a few ones that I think are the sort of major players in the area that are definitely worth looking at today. At first, I'd like to pitch a tool called Patroni, which is designed for automatic cluster management. So it sits on top of Postgres, and it manages a full cluster of Postgres nodes. And it does automatic failover, and does like replica attachments and things like that. It sits on top of either etcd, Zookeeper, or Consul, and sort of shifts off the heavy lifting to those tools, because using locked keys and things in them, it decides which is the master and lets them deal with the consensus of the cluster. And then it integrates that with the Postgres infrastructure tool to build replicas, promote standbys, rewind old standbys, and things like that. It also integrates with HA proxy, with the idea that you get an automatically working HA proxy config that you point your application at, and then Patroni will just update that config, and it has agents to talk to HA proxy to make sure it updates and that you connect to the right place. So particularly if you already have things like etcd or Zookeeper in your infrastructure, Patroni is a pretty good choice if what you're looking for is something that's like fully automated. I still like to say it's a little bit rough in some edges. It's a fairly new product in the space, but so far it works really well. I guess it wasn't the microphone. The other one that's really good to look at if you're looking at these scenarios is a tool called Rep Manager. It has a lot fewer prerequisites than Patroni. It's like basically self-contained. If you're installing from the Postgres yum repo or apt repo, you just do a yum install Rep Manager and you get everything you need. It is actually, I find it much easier to work with if what you want is manual systems, like just creating new replicas, repointing replicas, promoting and things like that. It does that well. It comes with a service called Rep Manager D that does automatic failover. I'd say today automatic failover definitely works better in Patroni. And while well documented, you can get into some really interesting scenarios with Rep Manager if you mix manual and automatic. Documentation says don't do that, but I know you don't read documentation. I know I didn't. And interesting things happened. And then I read the documentation and it said if you do this, interesting things will happen. So it was perfectly fine that way. Rep Manager doesn't handle connection management at all. You need to do that separately. You can use tools like Rebouncer, or you can use HA proxy with a little agent here as well. It's not in the Rep Manager bundle. But I would, if you're building replication clusters for some sort of availability, I definitely suggest that you look into one of these two tools rather than writing your own batch of shell scripts. Because I'm sure you'll get something wrong. Everybody gets something wrong when they do that. And the danger, of course, with getting something wrong in your HA setup is that, well, when are you going to find out that it was wrong? You actually needed it. We're switching back. Do I need two of them? Okay, we'll try. I don't think that's going to help, but we'll try. So, continuing upwards in the layers, database logical replication, which is something that we've sort of had in Postgres. We added a feature called logical decoding in Postgres 9.4, and the upcoming Postgres version 10, because this talk did say replication in 2017, right? And 10 will be out in 2017, I really hope. We get a built-in logical replication. Now, again, much of the infrastructure was there since 9.4. So we can still have that infrastructure prior to version 10, but in 10 it'll be built in. The idea behind this logical is that it piggybacks on the transaction log. So it's actually very similar to the streaming replication. It's just we add some more data so that we can do a logical level replication instead of just a physical level replication. This brings us the great advantage that this method also has very low overhead. So the magic to do this is, of course, you change your WAL level from replica and you make it logical. This adds the little bit of extra information to the WAL that we need. doing actual logical replication. The difference, logical replication no longer deals with disk blocks. When we're doing physical streaming replication, we replicate the actual changes to disk. In logical replication, what happens is there is a plugin that sits in Postgres and it reconstructs the changes row by row. So instead of replicating disk block, we replicate row contents. So we say, okay, you made an insert. We don't replicate the insert, but we replicate the row that the insert caused. If you make an update, we don't replicate the update. We replicate the new row of data and then the primary key of the old row. It doesn't have to be the primary key. We have something called a replication identity that we set on a table if you want something other than the primary key, but it's in some way we have to identify the row if we're going to be able to replicate an update, right? And same thing for deletes. We don't replicate SQL statements. We replicate the data. This, of course, means if you make a single update that updates 8 million rows, we will replicate 1 million rows. So it's a little bit less efficient than that, but on the other hand, you know that the content on the other server is going to be identical. This is all collected at the end of each transaction. So if you have a transaction that updates the same row multiple times, we can do merging and things like that. But it also means that at the receiving end, everything is fully transactional. This is one of the big issues if you're doing statement level replication, is trying to actually reliably reproduce that when you have multiple overlapping transactions on the receiving side is really, really hard. Somewhere between really hard and but if you do this, we replicate the data as it looked when you did commit. So obviously if you do a rollback, the data is never, the actual data is sent, but it's never part of the, we still have to write it to the transaction log, but we never use it. So it becomes fully transactional. And it gives us a bunch of things that physical doesn't give us. The way things that we get with a built-in logical today is we get table level partial replication. What does that mean? It means you can choose which tables you want to replicate. You don't have to replicate your whole cluster. You don't even have to replicate the whole database. You can pick individual tables and say, I want these 4 tables to replicate over there. It also supports table level bidirectional replication. Basically means you can have different tables replicating in different directions. Each individual table can still only have one master, but you can replicate one table from A to B and another table from B to A, right? So obviously this depends a lot on what your application looks like, whether that makes any sense. Okay, yeah, we'll see if that works. So you can do that, but you still, like, individual tables still only go one way. To use it, it's actually real simple. This is logical, so we do this at the database level. So in this example here, well, we create a table as usual, create table, test table. We got a primary key and a text field. And then we create this new type of object that is called a publication. And a publication is a collection of tables that are replicated as a unit. So in this case, I create a publication called testpub for the table, test table, and that's it. You can have multiple tables in it, obviously, and you can also create a special publication that says all tables, including all the future tables that I might add to this database. They should also be part of this publication. And you can configure your publication with different options. You can, for example, say that this publication is only going to replicate inserts. It's not going to bother replicating updates and deletes, because you might not care about that. That actually gives you a very interesting scenario for change collection on a standby. Say, replicate all the inserts and all the updates, but none of the deletes. Okay, so all your data stays on the standby. There are definite use cases for that. Then when you go to the other side, you create the same table, has to have the same schema, otherwise weird things will happen. And then you create this other new object that we have that is called a subscription. So in this case, on the standby, I'm creating a subscription called test sub. I give it a connection string that points to my master. And then I say publication test pub. So this means that my subscription test sub will connect to this publication that I just created on the other node. If I don't give it any other parameters, this is really all I need. Postgres is going to fire up a worker when I do my create subscription. It's going to connect to the master. It's going to copy the current data of the table, put that in the table on the standby, and then going to enable logical replication between these two nodes. Now there are same things here. We can add options to our subscriptions. We can, for example, tell it, don't bother doing the initial data copy. I only want the changes. I don't want the data that's in there now. Or maybe I already filled the data myself and then enabled replication and things like that. But for the simple case, create publication, create subscription, now you have logical replication. Well, you set your while level to logical initially, of course, in your config file. But that's really all there is to it. Now, there are some drawbacks to the logical replication that we have in Postgres 10. Number one, it's data replication only. It does not replicate schema, so if you do an alter table, things will break. That's something that's not that hard to deal with, really, at like an application level. It also doesn't replicate sequences. So if this table I had here, now this is just an integer, but if this had been a serial column, that would create a sequence. That sequence would not get replicated. You could still have it on the standby, it would have the same value. This means that, I mean, this is pretty suitable for data distribution, right? We want to copy our data around, but it really is not a solution for high availability. Because if you fail over and all your sequences still have the value 1, then your application is not going to work. Now, this is not a fundamental thing that logical replication can't have. This is just something that's not in the Postgres logical replication in version 10. Hopefully, we will be able to solve at least the sequence problem in Postgres version 11. The generic schema changes is a much bigger problem. Hopefully, we'll get there as well, but that might take a bit longer. We also don't support what is referred to as failover slots. What that basically means, if you have a streaming replication cluster with traditional block-based streaming as your master, and then you do logical replication from that cluster to something else. If you do a failover in that cluster, logical replication stops working. And you need to reconnect your subscriber. Heikki. Yes, if you say it should include all future tables, you still need to create the future tables. It replicates the data from the future tables. It doesn't replicate the create table. So if you use that, you should always create the table on the standby first, and then on the master, and then it starts replicating. So again, these are examples of cases where like the built-in logical replication, it's a new product, right? It's not even been released yet. There will be features added to this over many years and many releases to come. But this fundamental level of logical replication that we have in 10 is still going to be very useful at that level. Of course, if that level is not enough, there is an add-on product to Postgres called pglogical. It's actually been around a little bit longer. It's an external version of logical replication that still uses this logical decoding from Postgres 9.4. So it still uses the while level logical, it still has the efficiency of the logical replication. But it's a plugin. You download it separately, you install it on your master and your standby, and then you get access to some more functionality. Now the idea here is that basically the logical replication we have today has been ported over from pglogical into Postgres core. And there are many other features in pglogical, and the roadmap is that they will all be ported into Postgres core eventually. Like one by one, we're adding these things into core. pglogical has the advantage of being an extension, meaning they can evolve more rapidly. They don't have to be backwards compatible the same way. But it also means that it's not as deeply integrated, right? You don't do things like create publication. Instead, you call select on a function that will create a publication for you. It's like that type of a thing. pglogical today, it's not out for Postgres 10 yet, but it will be, at which point it will use the core replication from Postgres 10 and then just add their functionality on top of it. But you can also use this with 9.4 to get logical replication today. It does sequence replication. So they've solved that problem. We just need to figure out how to merge that back into Postgres. It does row-based filtering. So you can say only replicate the table where the rows match this where clause, for example. So you can get partial replication. It supports column-based filtering. Replicate only these columns from a table and get them over. It does merging and conflict resolution, where you can have multiple masters replicating into the same standby, into the same table on the standby. And of course, if you do that, then conflicting rows can show up, and you can configure what's going to happen with the conflicting rows. Now that's still not what most people would call multi-master, because it still only replicates in one direction. But it probably is the one that should be called multi-master, because it has multiple masters. It just doesn't replicate between the multiple masters. Of course, you can then combine that with the ability to do different tables in different directions and get a really, really complicated solution. I'd avoid that if I could, but it's good to have the ability to do that. So again, pglogical supports Postgres 9.4 and up, which is that pglogical is actually a very good choice today, as long as you're starting from 9.4 to get 0 or at least very close to 0 downtime upgrades. Because since it has the sequence replications, you can actually do high availability replication to a certain extent with it, which means you can run it from 9.4 to 9.6, for example, and have your system more or less live and just do a very quick failover on it. Because it's usually okay to say to your developers, you're not allowed to deploy new versions with alter table while we are upgrading the database. Like, you have to wait an hour until we're done. That's usually an acceptable thing. So if you need the more advanced logical replication, definitely check out pglogical. We will get there. We will get all of these things into Postgres core as well at some point. They're just not there yet. Of course, if we keep moving up in the layers, we get the application in database replication. So I said this is our typical trigger-based replication. These are things, who's ever used Sloaney? Who loved it? Thought it was really user-friendly? Yeah. Who's used Ricardo? Oh, no, nobody, that's unusual. Londiste? Yeah, you can tell which part of the world we're in, right? There are others. There's something called Ruby Rep. Anyone? There are a number of others. Basically, these all work the same. When you enable replication, they create a trigger on every table. Then every time you do an insert or an update or a delete, they copy that into a log table somewhere, saying, oh, somebody did an insert of this data. And then they have a little daemon somewhere that reads that data and reruns it on a different node. And that's sort of the core of how all these things work. They do it in slightly different ways, which is why we have more of them. But at the end, it's all triggers collecting data into a log table. Now that works. It comes with a lot of overhead, so we copy all the data just to begin with. But for a long time, this was the only choice. Like back in the days when people used to say, Postgres doesn't have replication, so we have to choose MySQL. Postgres did have several of these tools were around at the time, and they worked. But they had much higher overhead than the kind of things we're looking at now, and they're complicated to use. In particular, like Sloaney is a solution that supports ridiculously complicated topologies, and few other products for any database support that level of complicated scenarios. Now, most of you don't need that, and you still had to pay for some of that complexity, which is one of the things that gave Sloaney a really bad reputation. But it actually, like, once you got it set up, it worked pretty well. But today, these are mostly superseded, right? There are very few use cases where things like Sloaney or Ricardo or Londiste are the right choice today once you're on Postgres 9.4 or newer and can use this logical decoding stuff. Once you can do that, they're mostly superseded by pglogical and, as of Postgres 10, by the built-in version of logical replication. There are still use cases for them, and they're mostly in these, say, the very complicated scenarios. So they're still around. And of course, if you have a working cluster running on them, and the overhead is not a problem, well, it works. They're still being supported by the developers of the tools. So we do expect to see them around. And of course, the final thing that we can look as we go up the stack is that we have application level replication. You build the whole thing in your application, and you just assume the database can't do anything right. We're seeing a fair amount of these things happening today, and it turns out this is really, really difficult if your data is actually transactional to deal with that and making sure that all the nodes are updated correctly or unupdated and things like that. There are certainly limited cases where this is useful. Your database infrastructure is really simple when you do this, but on the other hand, you're re-implementing all these things in the application. And if you get sort of any level of complexity into it, you are almost certain to re-implement them badly. To be honest, that's what I usually reason when I look at this myself and I'm building an application and go like, I should fix this, and realize, people a lot smarter and experienced than me have written these other replication things. I'm going to trust those guys. It's also the database has a unique point where it sits between the application and the hardware. It knows about the data a lot more than the hardware, but it is a central point that everything goes through. So actually implementing these failover things at that layer is much easier than doing it in the application if you want to do it for the generic case. You can always do special casing things in your application, but normally that's not where you want to end up going. So, to summarize, if you want to solve the problem of high availability, use physical streaming replication. Use a mix of synchronous or asynchronous, or so, depending on what your needs are. Synchronous will provide you with greater availability, greater data availability. The cost for that is performance. If you're using synchronous, remember you always need at least 3 nodes, and you need an uneven number of nodes. Because if you have 2 nodes in synchronous mode, and your standby node goes down for some reason, then your entire system will freeze and basically become read-only. Because every write transaction will now wait for the standby that's down. So need 3. As of, in newer versions of Postgres, coming up in even further on that, Postgres 10 will add something called quorum commit. 9.6 added multiple synchronous standbys, so that you could say, I have these 5 servers, and I require my synchronous commits to hit 3 of them before I'm okay. Or 2 of them, or all 5, or anything like that. It gives you a lot of flexibility to control this synchronous level replication, which is really the knob you need to turn your availability replication, or tune your availability replication. That's really going to be how many syncs do you need, and which of these synchronous modes? Do you need local? Do you need fully synchronous? Do you need apply synchronous? Like which levels you need there. And I would strongly recommend that you evaluate, I'd recommend you evaluate both of Patroni and Rep Manager, and then you use the one that works best for you, that's adaptable to your environment and your needs. They're both very good, and they're both most likely better than you writing your own stuff. Because you will get something wrong. That's what most of us do. And I mean, I've written many versions of different failover management scripts for different customers. I'm really longing for these tools to get to like one more round of evolution where they become really easy to use, because then I can stop doing that completely. If the problem you're trying to solve is data distribution, well, if you're on Postgres 10, who's already running Postgres 10? In production? Just me? Come on. Maybe I don't run it on my most critical systems, but I do run Postgres 10 in production, and it works perfectly fine. If you're on Postgres 10, or if you're designing for Postgres 10, which might be the better question, you're designing for Postgres 10 today. If not, maybe you should be. Then use the logical replication that's in Postgres 10. It will be pretty well tested already by release. It's going to be the lowest overhead and the easiest to use logical level replication solution. If you're not on Postgres 10, then use pglogical and Postgres 9.4 or newer. Or if the built-in one in 10 isn't good enough, then use pglogical on Postgres 10 once it's available. If you're not on Postgres 9.4 or newer, well, upgrade to Postgres 9.4 or newer and you get pglogical. If you have a scenario where logical replication is an important part of your application, then quite frankly, upgrade to Postgres 9.4 or newer. pglogical and the logical decoding is that much better than trigger-based that alone should be a reason to upgrade Postgres. So upgrade away from your Sloanie, or like your Sloanie requirements, or your Picardo requirements, or whatever. They work, but they're nowhere near as good as the things that we're seeing in 9.4, and then again in 10, and as will be in upcoming distributions. So what if you need both, right? This is physical streaming and this is logical streaming. Well, if you need to solve both these problems, then use both, right? Use physical streaming replication in synchronous mode for your high availability needs, and make that the master of your logical replication. Now, unfortunately, yes, we have the issue with logical failover slots. It will be fixed. It's not fixed yet. If you use Sloanie on your master, on the database side, it works perfectly fine through this. You just need to remember to actually fail over the Sloanie processes as well. But like, these are solvable problems. But don't try to force one of these technologies to solve the other problem. Just use both of them. They're designed to be used together. All functionality is not there yet, but it is on its way. That's all I have. I think I've got about just under 5 minutes for questions. So, anyone?
So, do we have a question?
Hello, thank you for your speech. We found some drawback in logical replication. Imagine that there is a master server and we have some consumer logical and there is some lag on consumer. At that moment there is a high write load on master, so all changes for logical replication are stored in WAL. And load can be vacuum, create index, or something else. So all this WAL can be out of OS cache, so it is on disk only, and it is on, if specific load on server will be very high, it could be a situation when you would have a lot of WAL and lag will increase. Do you think about some another storage for changes for logical replication? Maybe we can, we replicate only few tables, not so big and not so many changes. Maybe we could make another storage for changes for logical replication.
So yeah, there has been discussions around like having the logical changes stored somewhere else. Actually storing them within the WAL has a huge benefit when it comes to transactional management. If you store them somewhere else, you end up having to basically do like two-phase commit between your two different transaction log things, which is very hard. Now, you're talking about the fact that you're replicating individual tables, for example, and that's even a more generic issue in some high-load installations of Postgres. If you have multiple databases, for example, they all have the same transaction log. So it might be that if we can solve that problem, then the problem of having the logical data in the same log will go away automatically. You have to store it somewhere, and the fact that you have to store these changes in a transactional way makes it really hard to move them somewhere else. I think the people who are building these things are well aware that you can run into this bottleneck, and obviously the bottleneck becomes much worse once your things start falling out of the operating system cache. Because once you hit actual disk, I think today most people just fix that by buying more operating system cache or faster disks, but yeah, that's not solving the problem, that is moving the problem. So yeah, I think that's one of the things that you will see today. Now, logical replication doesn't actually send all the data to the consumer. It only sends the parts that you're looking at, but it still has to pass through the transaction log. And if the transaction log ends up being your bottleneck, then yes, that is a drawback of the logical replication. But if you're looking at things like the trigger-based replication, that data also has to hit the transaction log because it's tables. So yeah, I think you've sort of just generally hit a generic performance endpoint with the current architecture, and it's certainly something that's being discussed on how to fix. I haven't heard anyone who's got an actual, like, working on a patch level solution for it yet.
And when you use trigger-based replication, all changes are stored in buffer cache, or maybe stored in buffer cache.
If you have enough RAM, but that's the same thing. If you don't have enough RAM for them to fit in the cache, well, then things will be slow.
One maybe last question. Sorry.
Hi, quick question. Does creating a publication add some additional load, and what will happen if we'll create publication but will not create subscription?
So adding the publication creates very little load. When you create the subscription, it creates a replication slot. That's when it starts actually actively tracking the data. So if you just create a publication and never create any subscription, it's not going to cost you much. But if you say create a publication and create a subscription, and then you kill the subscriber, but don't remove the subscription, then we're going to keep tracking all the data for it, and then that's going to be bad. So that's something you're going to want to monitor for. If you have any subscriptions where you just destroyed the machine without dropping the subscription, that's the part where the cost is.
One more question. The last one. It's true.
Do we also have time for an answer? Okay, good.
The question about logical replication and alter tables, for example, for adding a column. Suppose I can some way to stop processing at a master table and do similar alter tables on master and the slave in the logical replication. Do I need to recreate the replication, or it will up and running when I continue processing on the master?
You shouldn't need to drop and recreate. It should be up and running again. The problem is, of course, that you have to figure out how to block the updates on the master while you do that. And I think that's one area where we definitely need to improve the system, because we need to help you to do that part. But as long as the two tables are in the same format when the replication happens, then it will work.
Thank you.
Thank you.
So thanks a lot, Magnus.
Thank you.